Today we talk about mitochondria, not just the powerhouse of the cell, but possibly the drama queen of embryo testing.
I'm Dr. Mark Amols, and this is Taco Bout Fertility Tuesday.
Today's topic was sent in by a listener, and they want to know a little bit about MitoSure, which is one of the scoring parameters that are used when determining which embryo to transfer into a patient. So today, I'm going to take you on the scientific rabbit hole that's going to start with embryo selection and end with bacterial roommates. This is the story of MitoSure, a test that some thought was going to be the next big thing in IVF, but others felt it's more of a flashy sideshow. So grab a taco, maybe a shot of ATP, because we're getting into the Mito-Not-Sure if makes a difference episode. Now to start, what is MitoSure and why does it matter? Well, MitoSure is a test that measures the amount of mitochondrial DNA, also known as mtDNA, inside the trophectoderm cells of an embryo. And the way the theory works here, it's kind of interesting. Embryos that are under stress will start cranking out more mitochondria to compensate for that stress. Think of it like if a business was in panic mode and they started thinking about hiring more people to keep up with the demand. Now they're burning more energy just to stay afloat. Well, the same thing is the thought in the embryo. If it's under stress, it will make more mitochondria to make more energy needs. So the idea here is if an embryo has more mitochondrial DNA, it might be a sign that it's struggling. So the MitoSure test gives us a number that represents this mitochondrial load. A lower score might mean the embryo is kind of chill, doing well, it's ready to implant, whereas higher scores maybe not so much. But here's the thing. Unlike PGT-A, which checks for chromosomal abnormalities, MitoSure doesn't tell you anything about the genetics. It's a purely metabolic indicator. It's more like checking engine temperature, but not the blueprint of the car. Now, the good thing is it doesn't require an extra biopsy. So if you're already doing PGT-A, they can run the MitoSure score off of the same sample. Now, if you didn't get the nerdy ATP joke in the beginning, buckle up. ATP stands for adenosine triphosphate, which is the energy used in our cells. It's true that glucose is used to make energy, but it's the energy from ATP that is used in all the processes in our body. So to understand MitoSure, you have to understand mitochondria. And honestly, this is one of the coolest stories in biology. So a long time ago, and I mean really long time ago, like billions of years ago, a primitive single-cell organism swallowed a bacteria. And this bacteria could do something amazing. It could make energy using oxygen. So prior to that, the way bacteria would work is it would make energy not using oxygen. Now, instead of digesting it the way we would think of it more like it brought it in a symbiotic relationship and said, hey, why don't you stick around and keep making that ATP for me? So that bacteria, what we now call the mitochondrion, created a new relationship with this cell. So this means that every mitochondrion in your body is the descendant of an ancient bacterium that decided to become a roommate. This roommate didn't just stick around, it rewired the entire relationship. See, in the beginning, it started off making ATP by itself, but then eventually it started outsourcing most of the DNA to the host nucleus, becoming completely dependent. So now mitochondria cannot even survive outside the cell. They actually use your nuclear DNA to make some of the parts to make sure it runs. It's kind of wild when you think of it. Now, why mitochondria matter is because most cells, without the mitochondria, would only make 2 ATP from glycolysis, which is the breakdown of glucose. But the mitochondria could produce a ton of ATP. The full-blown oxidative phosphorylation powerhouse could make 30 plus ATP per glucose molecule. So when it moved in, it supercharged evolution. suddenly your cells could afford to get bigger, more complex, and start forming multicellular organisms, which include us. Energy is one of the most important things in our bodies. That's why we need oxygen and glucose to keep the energy production being made, and that comes from the mitochondria. So you can start to see why people thought seeing a difference in the ratio of the mitochondria might tell a little story about the embryo. Now, I appreciate not all of us believe in things like the Big Bang or that we all came from microorganisms, but from a scientific standpoint, that's what it looks like. And here's where it gets even more interesting. Because mitochondria are passed down only through the maternal line, all humans today can trace their mitochondria back to a single woman who lived in Africa about 150,000 to 200,000 years ago. And we call her the Mitochondrial Eve. Now, we don't think she's the only woman who was alive at that time, but the thought is that she's the only one where the mitochondrial lineage survived in all of us, and that's why we're all the same one. And animals also have their own Mitochondrial Eve. So your dog, cat, chimps, all of them have matrilineal ancestors too. So we don't share the same mitochondria with species, but they also have a Mitochondrial Eve as well. And if we go way, way back, we would find that all the mitochondria likely came from one bacterial lineage. So yeah, in some distant molecular family reunion, your mitochondria and a cow's mitochondria are cousins. Okay, now that I've gone on a far nerd tangent, let's bring it back to IVF. So back in 2015, a study showed that lower mitochondrial DNA levels in embryos were associated with higher implantation rates. And this was huge. At that point, it thought, okay, this may give us the answer of what are the best embryos to put back. But newer studies then hit the brakes on that. In 2019, they had studies that showed that embryos with high mitochondrial DNA still led to healthy pregnancies. And then in 2021, with a study with over 300 embryos, found that there was no correlation between mitochondrial levels and live birth. So as you can see, it wasn't a slam dunk anymore. Now it showed us that, yeah, it might be useful, but it sometimes might be a little bit noisy and not really help at all. So then the next question that should come up is, well, why isn't everyone using it? Is it because they don't think it works? Well, not exactly. That brings us to what are called platforms. Even though next-gen sequencing is a type of scientific method, there are different platforms that use it. There's one called Illumina, there's one called Thermo Fisher, and so the Thermo Fisher platform is built to handle short fragments of DNA, such as the mitochondrial DNA, and they're able to quantify it somewhat reliably. Now, there are other labs that have also very good NGS systems, but in their labs, such as Illumina, they aren't really optimized for mitochondrial DNA. So their workflow often filters out the mitochondrial reads by either not amplifying the mitochondrial DNA or not being optimized for it. What they do optimize for is what everyone's looking at, which is chromosomal aneuploidy, not metabolic markers. So as you can see, it doesn't make the labs inferior. They just are choosing not to do a test because their platform doesn't really go looking for it. But the funny thing is, even if they did, there really is no standard. See, when they do the test, what they do is they normalize it. So that way, what you're looking at is you're looking at a relative index versus an absolute copy number. Think of it like if we were looking in classrooms and someone said, oh, there's a 4-to-1 ratio between teachers and students. It doesn't tell you how many teachers there are or students, you just know the ratio. Well, the same thing here. You know the ratio of the mitochondria compared to some other number they're comparing it to, but it doesn't actually tell you the count. To make things even more difficult, each company may use a different number. So for example, you may be with a company like Progenesis that may be using a score of 2 as high, and another company that may be using a number as 18 or 20 as high. Neither of them are right or wrong, it's just they're using a different scale. Depending what their reference control is, it's going to change that ratio. They're still saying the same thing, they're just doing it through different ways. So in the end, labs don't use a standardized scale. It all depends on how they normalized the mitochondrial DNA data. So here's the $1,000,000 question. Should you use the MitoSure score? Well, whether you ask the embryologist or even if you ask the lab that did the test, what they're going to tell you is it shouldn't be your primary way of choosing your embryo, but if you are at a tiebreaker, it's a very useful test then to use. So this is saying if all things are equal and you have the exact same embryo with two of them, then you could use this to help break the tie. Another situation you could use it in is, let's say you've had multiple failed transfers, and you notice that a lot of the embryos have a high MitoSure score. It's not unreasonable to say, listen, these embryos are somewhat close, so although it's not definitive, maybe we'll put this embryo back has a lower MitoSure score, because in that situation, even the patient's best embryos aren't working. Now, what I can tell you is almost all clinics, including our own, still go by every criteria that we use for embryo selection before using a MitoSure score. It honestly is kind of an afterthought that we only use when it's absolutely necessary, such as a tiebreaker or a very unique situation. In the end, embryo morphology is going to be a better predictor of implantation than the MitoSure score. And that's because the MitoSure score doesn't tell us whether an embryo will implant. It doesn't guarantee success or failure. It's just one data point. It's a soft signal in a very noisy room. This is why, in most cases, we don't use it to guide our transfers. It just hasn't proven itself to be reliable enough. And this is probably why it creates so much confusion. Because as a patient, you think, well, here's this great test. It's saying something bad about my embryo. Why are they putting it back? But in reality, it's just not reliable enough. It doesn't consistently predict the outcome. And that creates a lot of confusion. So in the end, what's the verdict on MitoSure? Well, it's fascinating science. It teaches us more about our evolutionary past, about embryo metabolism, and maybe in the future might be a breakthrough. For now, it's more of a tiebreaker test. So it's important to use it wisely. Definitely question the hype if you heard about it. And it's most important to remember this. Just because we can measure something doesn't mean it helps us make better decisions. As always, thanks for listening to Taco Bout Fertility Tuesday. If you learned something new, subscribe to the podcast, tell your friends about it, but most of all, keep coming back. I look forward to talking to you again next week on Taco Bout Fertility Tuesday.